Well, my name is Cedric. I'm at King's College London in the same group as Mark. I should say this talk belongs to the interest group method. And by the way, I also take this opportunity to, well, first thank you all to attend the webinar series. And also maybe to contact me if you are interested to give a talk. We are looking for speakers who would be interested to show their activity during the TYC webinars. So here I will quickly just introduce something we released very recently called MOSCAM, which is a strange name, but essentially it's a dynamical mean field theory implementation in Onetype, which is a popular code that I'm sure most of you are familiar with. So let me try to move to the next slide. So it's a collaboration led by a former PhD student, Edward Linscott, who was at Cambridge, both with Mike Payne and Danny. Danny is now in Newcastle. And all this project has been a collaboration with Nick Hine as well in work. I'm sure most of you are familiar with Nick, Mike, and Danny. And also credit goes really to Edward, who was in a fantastic job putting things together. So what is the idea? Well, we're interested in extending what we learned in terms of method on periodic system. Typically, our usual codes are quantum espresso, VASP, K-step, and to extend that to the description of many body effects in a protein system or molecular system which are non-periodic. And a fantastic code to approach this kind of problem is Onetype, which has the advantage that it scales linearly with the size of the system you tackle with. You probably all know that if you do standard DFT, you essentially have to invert matrices, and this kind of operation scale with the cube of the number of orbitals. So Onetype is one of the groups belonging to this family. The other code would be a big DFT, for example, who uses a different basis. But these codes actually are very powerful in the sense that you can tackle large systems. But they still rely on DFT, and DFT, as you know, has issues for transition metal ions. So here is a screenshot of the recent preprint we have put online before Christmas. So the paper discusses essentially the functionality, an example that I will discuss in the next few minutes, which is the dissociation of heme from carbon monoxide. Some of the scaling is discussed, as well as some of the issues with the code. But essentially, it is an open source GPL plugin that you can use to with Onetype to extend Onetype to DMRT. So I encourage everyone to have a look at it if you're interested, and by all means try it or get in touch. I should say it's a very we reached that very recently, and still a work in progress. So we do anticipate that it's not as easy as click a button, but we are making a strong effort to black box it such that it is as transparent as possible in terms of usage. And okay, so I'll just discuss quickly the motivation. So transition metal systems are difficult because electrons are localized. And one example which is known is the localization through increasing a Mott-Hubbard U interaction from small u to large u, where you would essentially open a gap and in the middle have some emergent quasi-particle state. So these states are not contained, are not described well by DFT, and the idea is to add these excitations in a DFT calculation. In 30 seconds, the idea of DMRT is that you have a complicated system to start with, but you would like to simplify it. So a simple thing you could do is, instead of describing a spatially dependent problem, is to look at the local problem. So you have taken out just a single orbital or atom from your system, and you describe the rest of the system as an effective medium or reservoir. And the electrons will typically be flowing back and forth between the correlated atom and the reservoir, and this reservoir is obtained self-consistently to really mimic the best it can the rest of your molecule or crystal. And this is done dynamically in the sense that we have a notion of time, whereas standard mean field is really static, which is just essentially an order parameter, hence the name dynamical mean field theory. A typical Onetype workflow, if you're not familiar with Onetype, is essentially, as in most DFT code, to optimize the energy via the kernel. But Onetype also optimizes the basis set, which is a very powerful feature, as keeping the basis set as efficient as possible is really the key to obtain a fast convergence with a minimal Hamiltonian. So this is DFT. When you want to combine it with DFT, you essentially, DMRT, you always do DFT first, but now the new thing is that you are going to calculate Green's function and map this Green's function to what we call an Anderson impurity model, which is a quantum impurity model that describes the role of these local fluctuations. So this is an example of a sketch of this Anderson impurity model where you have essentially some impurity sites. These are your iron or copper atom, which is correlated, interacting with a bar sites. And the idea of DMFT is to solve exactly that problem in terms of both its ground state, but also excitations, which are contained in the Green's function, and extract from there the self-energy, which is a potential generated by local correlation. Again, I'm going very fast here and skipping many things as I'm aware of time. I have only 3 minutes left. So I'll just show you a few facts about the code. So first question is, how much does it cost to do DMFT? It's nice to have a better theory, but is it achievable in a code? Well, the fair answer is that you see here in this left side, the very thin line on the bottom is Onetype for the simple heme system. So a large portion of the overhead now comes from this extra work you're doing with DMFT. However, keep in mind here that this is applied to a very small molecule, and of course, the scaling of DMFT, the cost, the overhead of DMFT does not scale with the size of your system, provided that you have the same number of impurities. So think of hemoglobin or a system which typically have only a few correlated atoms. It means you can describe a large chunk of hemoglobin as long as you have a few iron correlated atoms only. However, it is quite a large cost, and this is divided by the different steps of the algorithm that we are using. The nice thing, however, is that it scales extremely well with OpenMP. We achieve until 8 threads nearly linear scaling, until 16 threads is not too bad. And it additionally scales also very well with MPI. So provided that you have large enough resources, that the task of solving this Anderson impurity model can be quite quick and typically obtained within 10 to 20 minutes. So that's the example that we looked at. Essentially, the idea was to benchmark a famous system, which is heme, the kernel of hemoglobin, where you have an iron atom in the middle, and how it actually changes its spin state as it dissociates from carbon. So heme bound to carbon is a singlet. You have a strong covalent bond, and as carbon goes away, you have a spin transition where you move from a singlet to a quintuplet. A problem with DFT is that this kind of spin transition are hard to capture at the level of DFT. You have many competing magnetic states, which are very close in energy. And DFT would actually obtain a triplet, however, very close to the quintet. So we did an extension with DMFT where you have the same transition, but now in DMFT, you don't only have a singlet or triplet states, you have some histograms or quantum entangled state. And you have to think of so here you have the iron-carbon distance. You have to think in terms of distribution of a quantum wave function into different quantum sectors, which involves all of the possible magnetic state from singlet to sextet and beyond. But you can see, however, in average, you do recover the same physics, but you start with a state which is a singlet contribution, doublet excited state, and triplet contribution. But then the higher spin sectors extend, and on the vertical axis, you actually see the weight of these different quantum sectors. So essentially, as you dissociate, the quintet and quadruplet sector expand. And this is why on the left side, you see that the average magnetic moment jumps up as you dissociate. So you do observe the spin transition. On the bottom left, on the upper left corner, you see the valence state of iron, which is going from 2+ to 3+ state. We are actually showing here also the pure DFT results, which are I'm colorblind, so for me it's always hard to spot this one. So the left triangle, yes, are here. So you see that DFT actually goes through the transition by steps, which is actually the best thing that DFT can do. It's trying to interpolate at the transition between the high and low spin state. However, it has to keep some finite magnetic moment, nearly integer magnetic moment. It cannot actually do like in DMRT, superpose state together. So this is why you have this intermediate plateau here. DMRT, on the other hand, on this pink circle here, goes smoothly between the high and low energy state, as you are just increasing the level of entanglement between the different magnetic state of iron. And this is now a continuous process. Okay, I think I will conclude here. I went quite quickly through the result, but essentially, yeah, so we call this, so we have a new release of a plugin for Onetype that we encourage the community to use if they're interested, called MOSCAM. We are building up documentation and providing an example. So one example is a simple dissociation of heme. DMRT is a plugin that can help you recover many body effects in a typical system that contains transition metal ion or rare earth or actinide systems. Applications are quite broad: molecular structure, metalloproteins, quantum biology. Quite generally, I would say multi-scale problems where you have some local correlations, but also some itinerant electrons that are interacting via correlated centers. Yeah, so I'll take any questions if someone wants to shoot.